Hello, my name is Frank McKenna. I'm here at UC Berkeley working for the Neary Sim Center. In this video, I'm going to demonstrate how we perform file I/O in the C programming language. So file, we're going to introduce now a new pointer type, a pointer to a file, something new. We get this pointer invoking the fopen function. Fopen and fclose are two new functions that you haven't seen before. The first one, of course, opens the file. The second one will close the file. There's some additional functions now for reading and writing to a file. We have fwrite and fread, and fprintf and fscanf. The fwrite and the fread are used to write large chunks and read large chunks at a time. The fprintf and this fscanf are to write formatted output, read and write formatted output. There are two additional methods that I'm not going to look at. They're reading individual characters. Typically in engineering, we're dealing with large chunks of data. We don't really care about the reading characters at a time. So the first two functions, fopen and fclose, are they're pretty simple. Fopen, you give it the file name, and you also give it the mode in which you want to open a file. There's three modes that we're going to look at initially. They are read, write, and append. So read opens a file to read from it. When you open with the W, you are opening the file to write to it. And what that is also going to do, if the file already exists, it's going to remove all the contents of the existing file. And then you can open a file to append to it, which is with an A. So if the file exists, you'll just start writing at the end of the file. And like malloc and free, fopen and close should always be used in pairs. If you fopen a file, you should always fclose it. If you don't fclose it when the program finishes, you will not necessarily have all your data. So here is hello world that will, instead of outputting to a screen, output to a file. Standard I/O, that is where fopen and fclose are defined. We first open a file. We set a file pointer equal to the return, what comes back from fopen. We then use fprintf. The first argument is that file pointer. And then the second argument is a formatted string. Because we're not providing any doubles, floats, or characters, we've no extra arguments here. And finally, when we're done with the file, we close it. Now, I'll point out that we've been using printf a lot in the course so far. fprintf is almost identical in format. The only difference is the first argument is always a file pointer. So all the printf things you've been playing with up to now, we can now quickly switch over to fprintf and just throw in a file pointer as the first argument. So here's a slightly more complicated example. We want to write a comma-separated file, say that MATLAB can open up and then do some plotting within MATLAB. So this is how we do it. We're going to open a file. Again, we're going to give it some file name. In this program, I'm passing the file name in as one of the arguments. And then we're going to open this file to write to it. I'm going to create a number of random variables, and in each line of the output, I'm going to put in an integer, followed by a comma, a space, a floating point value, another comma and a space, and then a floating point value, and then I'm going to terminate the line. The arguments I'm going to pass in are I, the loop variable, float1 and float2, the two random variables I've created here. And then when I'm done, I'm going to close the file. When I run this, GCC, I compile the file, then I'm running the file, specifying I want five rows. I want random variables from 0 to 1, and I'm going to want the output into file2.out. So if I have a look at the results when this file runs, this is what I see. So now we're going to read that file. So we're going to open the file again, fopen. Arguably, this program only takes one argument, basically the file we want to read. We're going to open it to read, so we put in the R, the string R. I create a float1 and a float2. I put some vectors into which I'm going to put the data. I malloc them, and I'm creating vectors of max vector size. And then while I'm not done, I'm going to read from the file using this formatted string, %d, comma, space, %f, comma, space, %f / newline. So that formatted string is identical to what we used in the write example. Then I'm going to give, we're setting values now, so I can't put in I float1 and float2. We have to put in the address of I, the address of float 1, and the address of float 2. And while we're going to keep doing this until we reach the end of file. We're going to set the vectors, and then we're also just going to print what came in. We're printing, actually, I made a mistake here. We're printing vector 2 before we print vector 1. Therefore, if I look at the output, yeah, I'll see that they are switched. So you'll see that these two columns are switched between what I'm reading in and what I'm printing out on the screen, and that's just because I've switched these two vectors here. And then when I'm done, I'm going to increment the vector size by 1, because remember, we're trying to read from a file 2 vectors, and we don't know the size of the vectors. Now, a problem I'm going to incur for a larger example is that if I hit max vector size, I have no longer allocated memory for for an array beyond max vector size, so problems will ensue if I start reading the data in and start writing to these vectors. So I'm now writing, once I go beyond max vector size, I'm now writing to memory in a spot that I have not allocated for these vectors. So I'm just going to start clobbering some existing data, and I'll keep clobbering it until I reach the end of the page that I'm in. If I reach the end of the page that I'm in, I'm going to page fault and kill the program. But if I don't reach the end of the page before I reach the end of the input file, I'm just going to have clobbered data, and I will not know that I clobbered the data. So I'm going to start getting these race conditions. I'm going to have different answers every time I run the program. Difficult to track down. So here I'm showing what happens. I've created a much larger file. I created this input file I created from file 2 was that we've got 1,000 floats in it, which is much bigger than max vector size, so that I did get a segmentation fault like I predicted. And as you see, it occurred at a number much larger than 100. We got up to 165 before one of these vectors tried to index a location that was on a page that the operating system had not allocated to the computer. Therefore, we get a segmentation fault. So as an exercise today, we are going to let you figure out what code needs to be here so that I can read in this vector. And it's very typical where you want to read some vector of unknown size in your program. So this will just be a little thinking on your part as to how to do it. So now writing to binary. So that was writing to an ASCII text file. Now what we want to do is write to a binary file. Why do we want to write to a binary file? Well, there's no data loss. If we're writing out floats versus, if we're saving floats versus writing out floats, we're actually going to have output that is half the size, because a float is 8 characters. A float is 4 characters. You'll see that when you write a binary, typically, it's going to be 8. You're going to get 8 characters. So now we have an example where we're going to write to a binary file. We're using this fwrite. So here we can write to output a large chunk of data at one time. So here is basically where I'm invoking the fwrite. So to use the fwrite, I have to open a file, and I want a WB, which stands I'm going to write a binary file. So here I'm opening this file binary pointer with the WB. I'm opening a binary file, and I'm also going to open the same program, open an ASCII file. So I just open that with the previously shown write. I randomly generate numbers for a vector, and then I put to the ASCII text file, as I've demonstrated previously, using a formatted string. I'm putting in a %f in a space. And now in this line here, this is where I'm writing my binary file, and I just write the whole thing to output at once. This is actually somewhat dangerous. I should have actually put this in a while loop, made sure I wrote the whole thing. So next time you see this example, I'll affix the code. We need to check that we actually wrote the whole file Otherwise we have to keep writing it in chunks. The reason that we have to write in chunks is this actually gets written to a buffer, and sometimes the buffer is full and we can't write the whole thing to it. So the program will only write a certain amount of bytes, so we have to come back again and try writing another set of bytes when that buffer has been emptied. So when we're done, we close both the binary file and the ASCII file. If we now look at the output, we see I've got two files. If I look at the ASCII file, we see the numbers that it generated, 5 numbers between 0 and 5, because I specified 5 numbers and I wanted it between 0 and 5. If we look at the binary file, which is the file 4.out, we see that I have a bunch of gobbledygook. But if we look at the size of the two files, I see that my binary file is half the size of my ASCII file. The reason is somewhat clear. If we look at this, we have 1, 2, 3, 4, 5, 6. So the file is written with 8 characters. These are characters, these aren't numbers. A character is 1 byte long, so that's 8 bytes. Now float, we've output 5 floats. Floats are 4 bytes in length. Therefore 5 floats are 20 bytes. So we see we've only got 20 bytes versus 46 bytes if we write it in the ASCII file. So last up is reading from a binary file. This is the inverse of writing to a binary file. So when we open the file, we're going to say we want to open a file where we're going to read from binary as opposed to write from binary. So it's read binary. When we're actually reading it, instead of fwrite, we're going to fread. We're going to put in the address of where we want at the start, if we want the data to go, the size of the data we're going to put in, the number of bytes associated with that data type, and finally, of course, the file pointer in which we're going to use to read the data from. What I'm showing here is a solution for the exercise.